wireless communication hides a surprising complexity under an incredible simplicity. To manage the high complexity, the communication flow has been divided into different layers, starting from the application layer up to the physical layer, where the analysis of the communication usually stops. We will go on exploring the world beneath the physical layer. In the deep physical layer, the laws of Maxwell rule the variation of the electromagnetic field in time, space, and polarization. Let's take a look at the space domain. In the harmonic regime, the field E on an observation curve C and the current distribution J on the antenna D are related by a continuous linear operator called the radiation operator that can be diagonalized using the Hilbert-Smith expansion. The coefficients of the representation of the current distribution are collected in a vector X which identifies an element in the Hilbert space. In the same way, the coefficients of the representation of the electric field are collected in a vector Y. The coefficients are scaled according to the singular values of the radiation operator. Let's take a look at the communication process as seen at the deep physical layer level. A specific bit sequence is associated with a specific current distribution. The coefficients of the current representation identify an element in set X which collects all the possible currents on the source. The radiation operator maps the X element into the Y element associated with the expansion coefficients of the field radiated by the current. The specific bit sequence is identified by observing the field associated with the element X. Different bit sequences are associated with different current distributions that radiate distinguishable field configurations. Noise and measurement uncertainty make it impossible to distinguish elements that are too close. If two elements are too close, the transmission fails. The maximum amount of information that can be reliably transmitted is fixed in the deep physical layer. Let us consider an example of data transmission in the space domain. In this example, the field radiated by a linear source in free space is observed along a line. The maximum amount of information that can be reliably transmitted is the solution to a sphere packing problem. In this way, it is possible to identify the largest set of currents radiating distinguishable fields. Each current is associated with a different sequence of bits. In the transmission process, the bit stream is divided into these sequences. The number of effective dimensions of the Y set of the field equals the number of singular values above the uncertainty level. This number is called the number of spatial degrees of freedom of the field and is a fundamental quantity that limits the amount of information that can be transmitted using the space domain. We have considered the Maxwell's equation of scalar harmonic regime. Let us introduce time and polarization. Also, for time and polarization, it is possible to introduce the number of degrees of freedom. The space-time polarization number of degrees of freedom of the field is a key quantity at the deep physical layer level. The number of degrees of freedom of the field is the amount of coins that the deep physical layer makes available. These coins are used in different ways in the physical layer to obtain specific transmission strategies.